Welcome to This Explainer. Today, we're diving into a genuinely fascinating engineering quest, which is teaching artificial intelligence how to watch, understand, and actually predict human motion. Now, we all know modern AI is brilliant at looking at a static picture and telling you exactly what's in it. But what happens when that picture starts moving? Well, as it turns out, things get incredibly complex.
Here's our roadmap for the explainer today. We'll start with the video challenge, move into splitting space and time, cover the 3D breakthrough, look at biology and bones, and wrap up with AI in the real world.
All right, let's jump straight into Section 1, the video challenge, adapting static networks to continuous motion.
To really understand this journey, we have to look at the fundamental roadblock engineers first face. How do you take a neural network that was built specifically for still images and adapt it to understand continuous video? Deep learning already had these amazing, highly tuned tools for pictures, so the core puzzle was figuring out how to optimally re-engineer them.
So here's the crucial point. While standard convolutional neural networks, or CNNs, are absolutely incredible at 2D static images, videos introduce an entirely new dimension that changes literally everything. And that's the dimension of time. Image processing just looks at static appearance and textures in a single frozen frame. But video processing, it requires analyzing chronologically ordered sequences. You have to capture both the spatial appearance of what's on the screen, plus the temporal motion dynamics of where it's going.
Moving right along to Part 2, splitting space and time, decoupling visual appearance from motion.
To solve that really tricky dimension of time, engineers came up with this ingenious divide-and-conquer solution called the two-stream framework. Instead of trying to force a single network to just do everything at once, they smartly decoupled the workload into two distinct parallel pathways.
Think of it like giving the AI two sets of eyes. One eye just looks at the static scene, and the other eye specifically tracks the literal blur of motion. The first branch is the spatial stream. It ingests a standard color frame, an RGB image, to understand the context, like the actors and objects. Meanwhile, the temporal stream ingests what's called dense optical flow fields. That's essentially a mathematical map of pixel displacement and motion philosophy. Finally, a class score fusion blends the independent probabilities from both of those streams to make a highly accurate final prediction.
Which brings us to Section 3, the 3D breakthrough, scaling data and inflating dimensions. As the field progressed, engineers naturally wanted to scan space and time simultaneously, but they hit a massive bottleneck with the data itself. Historical datasets were simply too tiny to train deep, data-hungry 3D networks from scratch. I mean, back in 2004, the KTH Actions dataset had just 600 videos. By 2012, UCF 101 had a bit over 13,000. But that was nothing compared to the millions of images used to train 2D networks. It wasn't until the crowdsourced explosion of the 2017 Kinetics dataset, which boasted over 300,000 videos, that massive 3D models actually became a viable reality. It was an absolute game changer for the industry.
Because training from scratch was so brutal before Kinetics came along, engineers developed an absolutely brilliant workaround, the i3D model. They essentially hacked an existing 2D network by inflating its previously learned image filters into the third dimension. They took all that incredible visual knowledge an AI had already learned from static photos and just mathematically stretched it out right across the time dimension.
And the numbers prove exactly how powerful this was. When you combine that 3D inflation technique with the massive Kinetics pre-training data we just talked about, accuracy leaps to an unprecedented 98% on the UCF 101 benchmark. It completely crushed the older baselines. Scaling the data and inflating the architecture unlocked a whole new level of machine perception.
All right, Part 4, biology and bones, mimicking human vision and stripping down to skeletons.
Now, heavy 3D pixel processing is incredibly accurate, but it's also highly computationally expensive. So engineers started looking at biological metaphors to make things faster. Just like human vision has different processing speeds, the slow, fast network mimics biology by cleanly separating visual context from rapid motion. Let's break down how this actually operates under the hood. The slow pathway ingests a low frame rate to capture strong, static spatial semantics. It's getting the big picture. Meanwhile, the fast pathway ingests a high frame rate, but it explicitly uses very lightweight channels to capture rapid temporal details without getting bogged down by heavy textures. Then, lateral connections explicitly fuse those fast motion features right back into the slow spatial representations. Why does this matter? Well, by keeping the fast pathway lightweight, a system, like an autonomous car for example, can process sudden motion instantly without paying the massive computational cost of heavy 3D networks.
Another way to gain extreme efficiency is by abandoning heavy video pixels entirely and boiling the data down to literal bones, using a pipeline like AlphaPose. Instead of looking at a massive grid of colored pixels, the AI runs a really clever three-step process. First, human detection draws localized bounding boxes around individual subjects. Second, pose estimation predicts specific anatomical key points to locate physical joints. And third, pose tracking links those generated skeletal graphs across consecutive frames over time.
Once you have those moving skeletons, how does the AI actually understand the action? By passing messages along these sparse, interconnected anatomical graphs using spatiotemporal graph convolutional networks, or STGCNs for short. Rather than processing a standard heavy image grid, the network tracks exactly how an elbow connects to a wrist and how that specific connection drifts chronologically. It's highly efficient and surprisingly robust.
And finally, Section 5. AI in the real world. Untrimmed reality and complex tasks.
Let's pull out of the lab for a minute and look at how these models transition from perfectly trimmed academic video clips to messy, untrimmed reality. Out here in the real world, models must understand long-term context to solve highly precise tasks. We're talking about tracking an assembly worker's specific hand movements in a continuous, multi-view video, or identifying exactly when a driver reaches for a laptop versus reaching for the steering wheel. This is known as procedural action segmentation and fine-grained activity tracking, and it requires deep, contextual awareness.
Amazingly, by fusing together multiple camera perspectives and sensory streams, like visible RGB light, depth maps, and infrared, models can now achieve nearly 75% accuracy when classifying complex driver behaviors in chaotic real-world environments. Fusing different physical sensors is absolutely the key to unlocking true situational awareness, which, as you can guess, is critical for things like building safe autonomous vehicles.
But the ultimate real-world challenge, and really the final frontier we're discussing in this explainer, is action anticipation. This requires the AI to forecast upcoming human movements based only on partial historical observations. It's not just asking the AI, "What are you doing right now?" It's asking, "What are you about to do next?"
To wrap things up, I want to leave you with a final, somewhat provocative thought to ponder. If an AI model can now predict your actions before you even physically complete them, what does the future of human-computer interaction actually look like? If machines can literally read the future of our physical intentions, how will that change our world? Thank you so much for exploring this deeply fascinating topic with me. I hope this structured journey through the evolution of action recognition really sparked your curiosity.